Okay, a vector is a quantity with direction. And we've talked about this before. When we first started our very first lesson, we talked about rays because there are two rays that open up to form an angle. So when you think of a vector, I want you to think of a ray where you have an endpoint and then it keeps going on in this other direction and you've got this arrow. The arrow tells you the direction that it's pointing. Okay, the only difference is with a ray and a vector is the vector actually stops at a point. There's an initial point and a terminal point. So you have an initial point and a terminal. Okay, if I call this P and this Q, right, that's my initial point and that's my terminal point, then the notation that you're going to use is PQ with an arrow. Your initial point always goes first. So your initial point is always going to be on the left like you're reading. Okay, so if it was set up like this, where Q was my initial point and P was my terminal point, then the notation would look like this. And a vector has magnitude and direction. The magnitude is the length of the vector, so the length from P to Q, or Q to P, depending on where you're starting. And the direction is going to be the angle that it swings open from the positive x-axis. Okay. If you have a vector that's in standard position, then that means the initial point is going to be at the origin. If it's in standard position, the initial point is going to be at the origin. That will be your direction, your angle that it opens up to. And then whatever length this is will be your magnitude. So let's say the terminal point is, just for an example, let's say the terminal point is 1, 2. If you write down your notation, if you're in standard position, because you start at the origin in standard notation, or sorry, standard position, then when you write down your notation for standard position, it's going to look like this. You're just going to write down your endpoint. It's going to look like that. Instead of having parentheses, you're going to have what looks like a greater than and less than symbol. That's your notation for a vector in standard position. So whatever this point is in here tells you your terminal point, and you just know that it starts at the origin, 0, 0. Okay, does anybody have any questions so far? Everybody's good? Okay. Okay, now to draw a vector, and we're going to draw it in standard position. Sometimes that's called the position vector. Okay, it says the initial point is at 2, 3. So I'm going to come over to 2 and up 3. And then the terminal point is 6, 4. So over 6, up 4. So here's my vector. We'll call it vector V. if I want to put this vector in standard position, we need to imagine, let me use a different color here. We need to imagine that this point, our initial point, is at the origin. Ooh, that's big. Okay, so we need to imagine that this point here is at the origin. So in order to figure out where my terminal point would be, just think about this as a triangle. I need to figure out where my terminal point is, so I'm going to come over 1, 2, 3, 4, and go up 1. 1, 2, 3, 4, go up 1. So we'll call that W. So just look at that like it's a triangle and go over and up. And just think of that initial point as being at the origin. That way you can draw it in standard position. So then if I want to write it, we'll call that vector W. Okay, how am I going to write this using my vector notation of fixing standard position? What am I going to put here and here?
4 and 1.
Yeah, 4 and 1. Because my initial point now would be 0, 0, and my terminal point would be 4, 1. Perfect. Okay, the magnitude and direction of a vector. Remember, magnitude is the length of the vector. So if we imagine that this is our vector, and I draw in dashed line to imagine my triangle, how could I find the length of this? Just think about triangles. How can I find that length? If I know, we'll call this A and this B. What is it?
Pythagorean.
Yeah, Pythagorean. Okay. So if I call this vector V and I want to find the length of vector V, now the notation for the magnitude or the length of a vector, it looks like absolute value. In our book, that's what it uses. In some other books, you might see it with like double absolute values. It means the same thing. Okay? So we're just going to take the square root of a squared plus b squared to find our length. We're just going to use Pythagorean theorem. A is called the horizontal component because it's going left to right. And B is called the vertical component because it's going up and down. Okay, now to find your angle, you're going to do inverse tangent. You could also use inverse cotangent, but it's much easier to use inverse tangent since we actually have that on our keypad on the calculator. Because we're using A's and B's, we're using our horizontal component and our vertical component. If I want to find this angle here, I want to use adjacent and opposite sides. And we can use cotangent and tangent for that. But we're going to stick with tangent since that's a little bit easier. So tangent is opposite over adjacent. So I take my B, my vertical component, over my horizontal component, and I do inverse tangent. The only thing you have to be careful of this is make sure you're in the right quadrant. So for example, if A and B were both negative, that means I'm in the third quadrant. So I want to make sure, even though tangent, inverse tangent would give me a positive angle in the first quadrant, I would want to make sure that I add pi to that to get the same answer that I would get as I would get in quadrant 3. So you also have to keep track of what quadrant you're in, just like every other problem that we've done. Okay, so just keep track of where your vector is so that when you do inverse tangent, you make sure you come up with the right angle. Okay, now, if we want to show that two vectors are the same, all we have to do is show that the magnitude is the same and the direction is the same. Show that magnitude and direction is the same. So what we're going to do is we're going to find the magnitude and direction for vector u and the magnitude and the direction for vector v, and if they're the same, we can say they're the same vector. Okay, so for the magnitude of vector u, we're going to do the square root of the horizontal component squared plus the vertical component squared. This is vector u right here, the one up here. Okay, what's my horizontal component? From here to here, what would that be? 5. So I'm going to do 5 squared plus, and then what's my vertical component? 4, yeah.
Sorry.
Better be sorry. So we're going to take 25 and 16, and that's going to give us the square root of 41. Okay, now to find the direction, we're going to do inverse tangent of the vertical component, which is 4, over the horizontal component, which is 5. That's going to give us, if you put that in your calculator, you'll get 38.7 degrees approximately. It'll come out to a longer decimal, but I think I rounded to one place. Okay, for vector v, that's this lower one here. To find the magnitude of v, we're going to do the square root of the horizontal and the vertical component squared. So what's my horizontal component here for v? So it stops here. Yeah, 5, so 5 squared. What is my horizontal component? 4. So I'm going to get the same thing. Now notice, which one of these is in standard position, u or v? Yeah, v is in standard position because it's at the origin. That's where it starts. Okay, now if I go to do my angle, I'm going to get the same thing because I'm going to do inverse tangent of 4 over 5, which I'm going to get approximately 38.7 degrees. Okay, now if we multiply a vector by a number, so if I have vector v and I multiply it by 3, that's what's called scalar multiplication because I'm multiplying by a number, not another vector. When I multiply a vector by another vector, that's called the dot product, and we're not going to get into that here. But if we multiply just a number times a vector, that's called scalar multiplication. And all that's going to do is it's going to make the length of the vector and stretch it out to that factor. So if I take 3 times v, it's going to triple the length of vector v. It's going to still have the same direction, but it'll just triple the length. So if this is vector v, then 3v might look like this. Okay, we'll take that length of v and we'll just stretch it out to 3 times that long. It will still have the same direction though. Okay, if I multiply a vector by -1, that's not going to change the magnitude, but it is going to change the direction. It's just going to go in the opposite direction. So what will happen is, if this, say, is angle V, or sorry, vector V, then negative V would look like this. It'll just be the same length, but in the opposite direction. Okay. Now, when we add two vectors, I'm going to give you an example here. If I call vector U 3, 5, and I call vector V -4, -2. This is vectors that are in standard position. So it's both of them are going to start at the origin. Vector U is going to end at 3, 5. So I'm going to come over to 3, up 5. There's vector U. Vector V is going to come out into the third quadrant at -4, -2. What happens is when I add these, it's going to create like a diagonal. And it's going to come up through the middle of those two vectors. And so U plus V, if I write it in component form like this, or standard form like this, I'm going to add the horizontal components, and then I'm going to add the vertical components. So 3 and -4 is going to give me -1, and 5 and -2 is going to give me a 3. So that would be my vector U plus V. Let me get a different color now. Let me do something a little bit brighter. So that would be -1. Excuse me. -1, +3. So it's going to come up here. And what I want you to do is imagine if I kind of finish this picture off, if I put those vectors head to tail, so I take V and I put U over here again, and I put V over here, the addition of that is going to come up across like a diagonal. Does everybody see how that works? Okay, that's going to happen every time for addition. Okay, you're going to complete the parallelogram, okay, kind of draw it off like each of the other sides, and then your addition of the two vectors, that vector will come up through the middle like a diagonal. And you can check it when you just add the components, so you add the horizontal components and you add the vertical components to check it, okay? For subtraction, it's basically you're just adding a -V. So you're just going to change the direction of V and then do addition. So let's see, if I use the example U is equal to 3, 5, V is equal to -5, 4. Let's use this example. So if I come over 3 and up 5, that will give me my terminal point for U. -5, 4 will give me my terminal point for V. Now, what would be my terminal point for negative v? So I know negative v is going to come down into the fourth quadrant because it's going in the opposite direction. What would be my terminal point then for negative v? Yeah, and a way you can check it is just multiply through by -1 too. You could check it that way too. So I would take -5 and multiply by 1, or sorry, -1, that would give me 5, and multiply 4 by -1, that would give me a -4. And you can see that gives me the same vector but in the opposite direction. Okay, so now we're going to add u and v. I'm going to do this in a different color, black. So I want to imagine that I'm completing this parallelogram, and the diagonal would be my u minus v. Okay, what would be my endpoint for u minus v?
8 comma 1.
Yeah, 8, 1.